All right, let's dive in. Let's talk about acids and bases. So, and the first part of talking about acids and bases is you just got to get the 3 different definitions for acids and bases. So 3 different sets of people came up with definitions for acids and bases. Mr. Arrhenius. So then came along Mr. Bronsted and Mr. Lowry. So, and then Mr. Lewis came up with the ultimate definition. So we got acids. So, and bases. So what did Mr. Arrhenius say was an acid? Proton donor in water, right on your sheet, right? So he looked at proton donors in water, whereas bases he looked at as being hydroxide donors, specifically in water. So Mr. Arrhenius only considered aqueous systems. Water had to be the solvent. So Mr. Bronsted Lowry, Mr. Lewis totally went a step further than that. So but only aqueous systems. And if you donate H plus in water, what do you get? H3O plus hydronium. So in this case, another way to state Arrhenius' definition here is say something that increases the concentration of H3O plus hydronium in water. So whereas a base is something that increases the concentration of hydroxide in water. So same diff. So Mr. Bronsted and Mr. Lowry came along and said, oh, Mr. Arrhenius, your definition sucks. What were you thinking? So, well, okay, your acid definition's okay. It's only okay, though, because whereas acids are proton donors, it doesn't have to be in water. They said you can use any solvent you want. This can actually even take place in the gas phase, and it still can be considered an acid. So, but they said your base definition kind of sucked. It's not about donating hydroxide. So we're going to look at this completely as the transfer of an H plus ion, a proton. So they said the acids do the donating, the bases do the accepting. And so the Bronsted-Lowry definition of a base is the H plus ion acceptor. Then Mr. Lewis came along. So in Mr. Lewis, he was kind of a shy guy, and he says, excuse me. So I think you guys might have made a mistake. So, because you've been talking about the protons, but it's really all about the electrons. And so an acid is not really a proton donor, but an electron acceptor. And a base is not a proton acceptor, it's really an electron donor. So when we say electron accepting and electron donating, it's not like redox. It's not like, losing electrons, gaining electrons, oxidation reduction. It's not in that sense. So let's say I was going to donate electrons towards Thomas. Then I would be the base, in this case Lewis definition, and he's going to accept them. He's going to be the acid. But I'm not just going to give them to him. I'm going to say, I'm going to make a bond to you. How many electrons are in a bond typically? 2. And I'm going to provide both the electrons. That's what makes me the donor. And you're just going to say, sweet, and accept that. So it's not like I'm just saying, here, have some electrons. So that's not what we're doing here. It's the base makes a bond to the acid. So, and that's the sense of donation here that we're going to talk about. So it turns out Lewis has the ultimate definition. Every single acid will always satisfy that definition. And every single base will always satisfy that definition. Now Bronsted and Lowry, their definition worked like 95% of the time. But 5% of acids and bases don't fit their definition. It only fits the Lewis definition. So, and then Arrhenius's was the most incomplete. But every Arrhenius acid will also be a Bronsted acid, and every Bronsted acid will also be a Lewis acid. But you should know a few of the Lewis acids that don't qualify under the other 2 older definitions that are a little incomplete. So, and you'll see things like BF3, so, or maybe AlCl3. Those are 2 good examples of Lewis acids. But why can't they satisfy either the Arrhenius or the Bronsted-Lowry definition? They don't have H+. There's no hydrogens. How can they donate hydrogen? What rule is boron and aluminum? What rule are they infamous for breaking, for violating? Octet rule. And they have an empty p orbital. So no filled octet. And they would just love for somebody to donate electrons and make a bond to them. That's what makes them a great Lewis, great Lewis acids in this case. But they don't satisfy either of the other definitions. They only satisfy the definition of an acid according to Mr. Lewis. So the other one in general, metal ions in general can act as Lewis acids. So metals, what charge do they typically take? Positive or negative? Positive. Metals typically form cations. Being cations, metal ions, therefore, would love to attract, to accept some electrons. So boron and aluminum compounds, but metal ions in general often act as Lewis acids. And again, we're just talking about like, Pb4 plus or Pb2 plus or Sn2 plus or, any one of these metal ions can potentially act as a Lewis acid, but they don't have H, so they definitely can't satisfy any other definition besides Lewis's. Cool, so those are your big exceptions. So most of the Lewis bases would also satisfy at least Bronsted Lowry's definition. So, cool, questions on the definitions here. You should know the definitions because you may just simply get a question about, what's the definition of a Lewis acid, or which of the following is true about a Bronsted Lowry base, or something like that. But you should also know that these guys are the ones that satisfy only Lewis's definition of an acid, because you often get a question that just simply says, which of the following is a Lewis acid specifically, and only a Lewis acid, or something like that. Question?
Do they not have conjugates? So like BF3, it's conjugate base.
Cool, we wouldn't usually talk about conjugate bases in this context. When we talk about conjugate acids and bases in a little bit, we'll only talk about it from a Bronsted Lowry perspective. Technically, we could potentially do it in an absolute sense, but not in this class. So only do it for the Bronsted Lowry side, though. Cool, any questions before we move on? So we're going to talk about strong acids and strong bases. And the first thing I need to know is, what do we mean when we say that an acid is strong, or that a base is strong? What does that actually mean? Dissociates completely. So it dissociates in water virtually 100%. So in this case, how many strong acids do you have? You got 7. So and I like grouping them together so it makes them a little easier to remember. But notice HCl and HBr, HI go together, but notice HF is not on that list. So be careful with HF, not a strong acid. So then you've got HClO4 and HClO3, they go together. So, and then sulfuric and nitric, they don't really look like they go together, but they're very commonly found in most chemistry laboratories. In fact, we often mix these two together, and it's just simply called mixed acid when you do that. So, but there's your 7 strong acids. They dissociate completely in water. And notice HF is not on this list. The reason we often think of HF as being, strong or something like that, even though it's not strong, it's just deadly. So if you spill a little HF on your arm and you don't notice that, I'll dig your grave. Call the mortician, because we'll be burying you sometime in the not so distant future. So, but it's not because it's an acid, it's because it has fluoride in it. So, and I know fluoride's good for your teeth and all, but not in this form. So in this form, why is fluoride bad for you? Anybody know? It sucks all the calcium out of you. It leaches calcium out of you. Why is that bad? So it's not about your bones. That's not what kills you. So, but although if it had the chance, it would do that too. But it leaches it somewhere else first. Out of your bloodstream. Out of your bloodstream. And calcium's just responsible for some minor things like, regulating your heartbeat, your body temperature, and just other minor stuff like that. So, but yeah, you get exposed to HF for any period of time, it'll leach right through your skin and cause you really bad problems. But it's not a strong acid. Deadly, but not strong. Only dissociates partially. But these 7 all dissociate completely in water. In fact, if they dissociate completely in water, so if you have HCl and you put it in water, how many intact HCl molecules will you have in that solution? 0. What will you have instead as your acidic species at that point? H3O plus. In fact, all of these, you put them in water, and what will be the only acidic species pretty much present in that solution? H3O plus. We call that the leveling effect. All of these dissociate completely. And so it doesn't really matter which one you have. As long as you have an equal concentration of any of these, you'll roughly have an equivalent, an equivalent acidity in each of those solutions. They call it the leveling effect. So one thing to note, H2SO4 is the only polyprotic strong acid. It has more than one acidic proton. In this case, we call it diprotic specifically. However, only the first H dissociates completely. Strong bases. So when you think of a classic strong base, what do you think of? So more specific, give me a more specific example. NaOH. By far the most common strong base students learn about, right? So, but it's actually all the group 1 metal hydroxides. So LiOH, NaOH, KOH, rubidium hydroxide, and cesium hydroxide makes the list as well. So francium would make the list, but francium is really radioactive, and we just never mess with it in normal chemistry. But at the bottom of the group 1s, yeah, if we decided to really mess with francium hydroxide, I would let one of you do it, so you could be the one getting cancer instead of me, but it would technically be even stronger than all of these. So, and then for the group 2 hydroxides, calcium hydroxide, strontium hydroxide, barium hydroxide, the 3 biggest ones that aren't radioactive anyways. So we don't usually include magnesium on this list. Some people will put magnesium on here, but magnesium hydroxide is not all that soluble, and so most books won't put it on their strong base list. So and truth be told, I mean, calcium hydroxide's only got a kind of an intermediate solubility. And as far as it's soluble, the part that's soluble does dissociate completely. So it's kind of a tricky thing, but we'll consider these all as dissociating completely. Now, one thing to note, whereas H2SO4, only one H dissociates completely, for these 3 strong bases, both hydroxide ions dissociate completely. So note the difference here. If you have 0.1 molar, let's go with HCl first. You have 0.1 molar HCl. What hydronium ion concentration do you get? 0.1, dissociates completely. So if you have 0.1 molar H2SO4, what hydronium or hydrogen ion, same diff, concentration do you get? 0.1. Sort of. Almost exactly 0.1, but not quite. Why not exactly 0.1? Well, it turns out the second H is weakly acidic. Not strongly, doesn't dissociate completely, but it does dissociate a tiny little bit. And so instead of 0.1 molar H2SO4 having 0.1 molar H+, it's just a teeny bit higher than 0.1, but pretty close to 0.1. So, but here, if you have 0.1 molar NaOH, what's your concentration of hydroxide going to be, OH minus? 0.1. But if you have 0.1 molar barium hydroxide, what's your hydroxide concentration going to be? Twice as much, 0.2 molar in that case, and that's your big difference. So the strong bases that have 2 hydroxides dissociate completely, both hydroxides. Cool, you need to memorize these. These are your strong acids and bases. So if I give you any acid that is not one of these 7, you can by default know that it is a weak acid, just because it's not strong. How can you recognize an acid? It starts with an H, or if it has acid in the name. Pretty much your big ways to recognize an acid. So any acid that's not one of these, it's going to be a weak acid by default. Weak acids only dissociate partially, usually less than 5% in most cases. So and it turns out the higher the concentration, the less they dissociate. The lower the concentration of weak acid, the more they dissociate. It's kind of a weird thing. So cool. Any questions before we move on? Okay. Let's talk about a couple of different types of acids. So binary acids. What do you suppose a binary acid is? What do you suppose the word binary means?
It only has an H and another molecule.
Good, H and another element.
Yeah.
So only has H and another element. Their binary acids are only composed of 2 elements, H and one other. So if you notice, is HCl a binary acid? You bet. Is HClO4 a binary acid? No. So, and it doesn't have to just have one H. So HCl, HF, HBr, HI. So technically H2O, H2S, if we wanted to include it on the list and stuff like that, those are also considered binary acids. It's still just 2 elements, even though they have multiple hydrogen atoms. So, but we can do a binary acid of just about any of the nonmetals. Question?
I'm sorry, maybe I missed that. Did you say that H2O was an acid?
So H2O can be termed an acid. It's not the most acidic thing, right? We'll actually find that H2O, water, is amphoteric. We'll come to that in a little bit, but it can act as an acid or a base, but it's not really the most acidic or the most basic compound in and of itself.
And then my other question is, why wouldn't H2O then be the oxoacid or whatever?
So an oxoacid is the acid of an oxoanion. So notice an oxoanion is a polyatomic ion with oxygen. So if we look at water, it doesn't have a polyatomic ion in it, but notice HClO4 is the polyatomic oxoacid, if you will, so of the polyatomic ion perchlorate. this is also an oxoacid. These are both also oxoacids if it's derived from an oxoanion. But H2O is not. It's just considered binary. Okay, the trend here. So is that binary acids get stronger going to the right and going down. So that is your binary acid trend. So, and if you look, they get stronger as you go to the right. So notice if you were to compare, say, water and HF. Well, what do you know about water? Yeah, it's kind of neutral, right? pH 7, it's not the most acidic compound in the world. But what do you know about HF? It's a weak acid, a genuine weak acid. Its pH will be lower than 7. And so, yeah, he's stronger than he is. Why? Electronegativity is our big reason. So as an acid, as the other atom besides hydrogen gets more electronegative, it gets more acidic. Cool. So if we look, as you go from HF to HCl to HBr to HI, 3 of those are strong, but 1 of them's not. In this case, if there's a trend then, if HF is weak and these 3 are all strong, the trend must be they're getting stronger as you go down. Why in this case? It's about size. What about size? Awesome. So the bigger it is, the longer, weaker bond with hydrogen. And if it's a longer, weaker bond, it'll break, dissociate more easily. Cool. So what's more important, size or electronegativity? Well, if we look here, HF, HCl, which one's more acidic? HCl. Which one's more electronegative? Ooh, F. I got a problem. So what's more important, size or electronegativity? Sizes, it turns out. So if you're comparing them in the same column, it's all about size. But when you compare the binary acids in the same period here, so they're all very similar in size in the same period. And so that's when electronegativity is what your basis of your comparison. Cool. Any questions about the trend for binary acids? Okay. Also got a couple of trends for oxo or oxy acids we got to talk about. You'll see these called oxoacids or oxy acids, same diff. And you got 2 rules here. And the first is more oxygens, more acidic. So this would help you figure out that like HClO4 is more acidic than HClO3, which is more acidic than HClO2, which is more acidic than HClO. And in this case, you probably knew that anyways, because these 2 are strong and these 2 are weak. So if there's a trend, it must be the ones with the most oxygens are the most acidic. So if you know your strong acids, they can go a long way to helping you remember some of these trends. So the reason here, it turns out, so when an acid dissociates, it gives away an H+, and you're left with the conjugate base. The more stable that conjugate base, then the easier it is to form it, to dissociate and form it. And so a more stable conjugate base comes from a stronger acid. And in this case, the more oxygens you have, the more stable the conjugate base is going to be, because it'll be stabilized by, it turns out, resonance. So if you've got to come up with one word that explains it, it's actually all about resonance in this case. May not have been something that Dr. Searley touched on. She did a little bit? Okay. So the second rule. It's all about the hetero atom, I'm going to call it. So, but the more electronegative hetero atom, talk about what that means in a sec, but more acidic as well. So when I say hetero atom, what do I mean by hetero first off? Different. So all oxy acids will, because they're acids, they have to have what element? Hydrogen in this case. But because they're oxy acids, they got to have oxygen as well. The hetero atom is just the other element besides hydrogen and oxygen. So like in H2SO4, so the the hetero atom in H2SO4 would be sulfur. So in HClO4, the hetero atom would be chlorine, so on and so forth. And so here, the more electronegative the hetero atom, the more acidic it's going to be. It has nothing to do with size in this case, it turns out. It's only electronegativity playing an impact here for the oxyacids. Again, the binary acids, size played a role and electronegativity played a role. But for oxyacids, only electronegativity matters. And so in this case, we could use this to figure out that HClO4 is more acidic than HBrO4 is more acidic than HiO4. Because they all have the same number of oxygens, so that's when this comparison becomes relevant. And in this case, chlorine is more electronegative than bromine, and bromine's more electronegative than iodine. Hence the trend. Nothing to do with size whatsoever. So this gets confusing. So, because if you just compare Hi and HBr, binary acids, which one's stronger? Hi and HBr, which one's stronger? Hi. But if you can compare HBrO4 and HiO4, which one's stronger there? HBrO4. So it can seem somewhat confusing, but they're two different types of acids in this case. Cool. Any questions right here?
In your example of the polyprotic acids, you said like H2SO4 and H3PO4?
H3PO4 would be another example.
Well, but the H2 and the H3, doesn't matter how many hydrogens you have when you're comparing?
Nope, not at all. Not at all.
Just the oxygen, as long as all the oxygens are the same.
Correct, correct. All right. Let's talk about polyprotic acid. Oh, question.
Yeah, so for binary acids, does size matter than electronegativity?
Correct. But here, you first look at the number of oxygens, but if that's the same, size doesn't matter here at all. It's all about electronegativity.
Okay, but you're ranking oxygens ahead of electronegativity.
Correct, correct. So check the number of oxygens first. And they're not going to give you a trend where like, well, this one's more electronegative, but this one has more oxygens. They can't do that to you, except in one example. The only time they can do that to you is if one of the acids they're having you compare is strong and one of them is not. Well, then you should know that answer as well. Which one's stronger? The strong one. Let's talk about polyprotic acids for a minute. So we'll first talk about the only polyprotic strong acid that you guys are going to talk about, H2SO4. And again, if I put it in water, how much is it going to dissociate? Yeah, virtually 100%. So, and you get H+, and after an acid donates away H+, you're left with his conjugate base. So, and you should be able to, if I give you an acid, write me the formula of its conjugate base. If I give you a base, you should be able to write me the formula of its conjugate acid. And we're always looking at it in this context from whose perspective? Bronsted Lowry. So an acid's an H+ donor, so after he gets rid of the H+, what do you have left? That's the conjugate base. But this thing itself is still acidic. It's only weakly acidic. So in this case, I probably should more reflectively here write that as completely. But this one's only going to dissociate partially. And so in this case, what will I get as products? H+, and then what's the conjugate base of him? Good. So if I want to ask you a tricky question about what's the conjugate acid of blah, or what's the conjugate base of blah, I'm going to give you a compound like him. Because he could act as an acid, and his conjugate base is right there. But he could also act as a base, and his conjugate acid is right there. And so he's what we call amphoteric, or amphiprotic. So because it can act as an acid or a base. And so if I want to ask you a tricky question about what's the conjugate acid of something, or what's the conjugate base of something, I'd probably do something like this because it could go one of two ways. So be careful. All right, if we look at a solution of H2SO4 then, so say I've got a big fat beaker of water with H2SO4 dissolved in it. My question is, besides the water that's in there, what species will be present in the highest concentration? Well, let's go the other way. What species would be present in the lowest concentration? We can probably answer that one. Of all the species listed on the board, yeah, for sure. How much of this should I really technically have left? Virtually none. So if we rank these then, his concentration should be at the bottom end. Everybody should have a higher concentration. There should be no negative there. So everybody should have a higher concentration than he does. Okay, so here's the deal. When you have a polyprotic acid, they get less acidic the more protons they've already donated. So after he donates one, and that's strongly acidic, donates it completely, then he only donates the next one to a small extent, partially. So in a polyprotic acid sequence, it always gets less and less and less acidic. We'll talk about Ka's in a little bit. The Ka always gets lower and lower and lower as you go further down the sequence. So in this case then, let's say we started out with 1 million H2SO4 molecules. Well then, how many of these would I end up with? 1 million of each. But whereas I'm still going to have all million of those, I'm not going to keep all million of these. A small fraction, maybe 1 out of 100, is going to dissociate further. So 1%, let's say. Okay, if 1% of these dissociate, that means 10, let's see if I do this right, 10,000 of them are gone. 990,000 of them are still around, but 10,000 of them dissociated to give 10,000 of those and 10,000 of those. So notice, you originally got 1 million of both of these, but this one's down to 990,000. But technically, you just produced some more H+. You got 1 million from the first dissociation. You just got another 10,000. He is present in the greatest concentration. Who's present in the next lowest concentration after H2SO4? The SO4 2-. You only got 10,000 of these. In this case, my kind of quasi-example. Cool, and then which of these two do you have more of again? H+. We didn't lose any in this process, we gained a little more actually. And so in this case, next in the sequence would be HSO4-, and then H+. Cool, and you may get a question that says, in a solution of H2SO4, which of the following shows the relative concentrations of all species? Well, there you go. There's your answer. So let's say we dealt with a weak polyprotic acid, in this case phosphoric acid. And in this case, it could dissociate the first time. And what's the conjugate base of H3PO4? Yeah, H2PO4-. But then that could dissociate, give you another H+, and what's the conjugate base of H2PO4-? Notice you're getting rid of an H and you're getting rid of a plus because it's donating H+. So get rid of an H and you only have HPO4, but you also got rid of a plus charge, which what total charge would that leave you with? 2-. Cool. But you still got one hydrogen you could further donate. And so what's the conjugate base of HPO4 2-? Yeah, PO4 3-, the phosphate ion. So now we got a little bit longer sequence in this case. And it's going to be a little bit different because, is he strong? No, he's weak, which means he's only going to associate to a very small extent in most cases. So if we look at this then, so a couple of things is we have 3 acidic species here, H3PO4, H2PO4-, and HPO4 2-. Which one of those 3 is the most acidic? Yeah, the one with the most H's. So once he gets rid of one H, it's harder to get rid of another. Once you get rid of another H, it's harder to get rid of another. Let's say I deposited $3 million in your bank account tonight without you knowing it, and you woke up tomorrow and there was $3 million in your bank account. Good day, right? So one, I wish I had $3 million to stick in your bank account. So, but a good day. But let's say later in the day, I decided, nah, I'll take one of those millions back. And so you only had $2 million left. Are you pissed? No, you still got $2 million, right? And later in the day, you only had $1 million left. And you might be like, well, wait a minute. I still got $1 million. So, but later in the day, I go in to take the last $1 million. But you're wise to me now, and you cut me off at the bank, and you say, take my last $1 million and I'll kill you. So you're not willing to give up that last $1 million, and kind of analogously here, once the acid give up H's, it gets harder and harder to give up another one. So if we were ranking the Ka's here, out of the 3 acidic species in the sequence here, H3PO4 would have the highest of the 3 Ka's, and HPO4- would have the lowest of the Ka's. So we'll see that a higher Ka means more acidic and a lower Ka means less acidic. Okay, if we look here, which of the species present should have the lowest overall concentration. Yeah, well, it's not the first one this time. Because how much does this dissociate now, Thomas? Not much, which means actually I might have a lot of this left in my solution. In fact, he'll be present in the greatest concentration because less than 5% of him probably dissociated. So I'm only going to get a little bit of these, and I'm still going to have a lot of this left over. But once I get to the end, I get a little bit of these, and of the little bit of these, a little bit of that for the dissociates, to get even less of these. And of the teeny tiny amount of these I got, even less dissociates to finally get all the way down here. That's why he's the lowest. And so in this case, we got our extremes. We definitely have, at one end of the spectrum, PO4 3-, and at the other end of the spectrum, H3PO4. So, but who's present in the next highest concentration? H+. When H3PO4 dissociates, you get an equal amount of both. But then you're going to lose a little bit of this, and you're going to keep gaining more and more H+ all along the way. And then? And then? Only guy left. Awesome. Cool. And this would be the relative concentration order for all the species present in a solution of phosphoric acid.